Hi Wildcats, this is the introduction to Unit 4. Unit 4 is on electrostatics, electricity, and magnetism, and we're going to talk specifically about Unit 4 focus question 1, which is about electrical charges, specifically why do different materials respond to electrical forces in different ways. So let's start by talking about this unit in general. This unit is about electrostatics, electricity, and magnetism. So we really want to think here about what those are. And I think a common example that we're all familiar with is electricity in lightning strikes, right? So, what exactly is happening there? I think this picture is a pretty simple representation, but we can see that a cloud, a storm cloud, has a whole bunch of electrical charges, negative electrical charges, and the Earth is positively charged. So when we talk about electricity, we're really just talking about, or a lightning strike, which is electricity, the movement of those charges. And we're going to talk and review a little bit about opposite charges. But one thing I think we know in general is that opposites attract, right? So if a cloud is negatively charged and the Earth is positively charged, then at the most fundamental level, those electrical charges or the negative charges will be attracted to the Earth, hence lightning. So we need to start with a little bit of a review of atomic structure. So first, all matter is composed of atoms, and atoms have three main parts: protons, neutrons, and electrons. And we represent them. Protons are represented with a positive charge, neutrons are represented with a zero or an O for no charge, and electrons we represent with a negative sign. Just to review as well, inside the nucleus, we have protons and neutrons, and they're bound really tightly inside the nucleus, whereas electrons are loosely bound and go around the outside. Because of that, the number of protons and neutrons in an atom doesn't change really. It's the same number. What does change about an atom is the number of electrons that it has. And electrons can be shared or moved in between atoms. And so, like in chemistry, you might remember HCl. So in this case, the hydrogen atom has an extra electron and chlorine is missing one, so they actually share, they bond together, right? That's a chemical bond where they're sharing those electrons. Or another example, like in NaCl, the electron is actually moves from one to the other, so we end up with Na plus and Cl minus. So those are just examples that hopefully you recall from chemistry class where we see electrons moving or being shared, whereas protons and neutrons don't. And that's really going to become important in our understanding of electrostatics and electricity. So, continue our review. You may remember that there are things called valence electrons. So, valence electrons are the outermost shell, and different depending on the atomic number of an atom, it has X number of electrons, protons, and neutrons. And then, so we start with 2 in the first shell, and then 8, and so on and so forth. Those are called octets. And what we find is that some atoms have an odd number, like they just end up with one extra electron in their outer shell, and this outer shell is not full. And so, if you recall from chemistry, quote unquote, for atoms to be happy, atoms can't be happy, but to be most stable from an energy standpoint, they want an outer shell that is full of electrons. And so this copper atom has one extra. So whereas other atoms like xenon here, its outer shell, if we counted these, has full. It has its octet as 8. And so this is more stable than this. And what that means is that atoms like copper can easily give up an electron because it makes them more energetically stable, whereas xenon is quote unquote content, more stable where it currently is at. And that, at the most fundamental level, those different atomic or molecular structures is what ultimately causes different materials to have different properties. And so what we call them are conductors and insulators. So conductors are made up of materials that have atoms that will easily move. So there's a reason that the electric wires that we use in our houses are copper. Copper has that one extra electron in its outermost shell, and because of that, copper will easily give up this electron, which means the electrons can move. if we go all the way back to our beginning slide here, movement of electrons, these negative charges, is electricity. So when we want charges to move easily, or materials that are made up of atoms that have extra electrons that they'll easily give up, are called conductors. Materials that are made up of atoms that don't easily give up their electrons are insulators. And so glass is a really good insulator. Well, glass is like this big complex molecule filled with all these stable bonds, and electrons don't move easily through it. And that is why, same thing like wood. Everyone knows wood is an insulator. Well, it's a big complex molecule with lots of bonds that keeps all the electrons in place, whereas copper wire can give up those electrons easily, slash electricity can move through it easily. So that's a little review on the different properties of atoms and why some are better than others at transferring electricity. Okay, so what determines if an object is electrically charged? Well, ultimately it comes down to the number of electrons surrounding the nucleus determines if it's charged. If it has more electrons than protons, or fewer electrons than protons, those are ions. And so those things would be electrically charged. Those atoms would be electrically charged. Whereas if I have an equal number of electrons and protons, there is no charge. So we really want to say this is the cumulative or net of number of charges that produces an electrically charged atom or therefore material. So we can say things like this atom has 6 protons, 6 neutrons, and 6 electrons. So overall, it has no charge. Over here, 6 protons and 7 electrons means this is going to have a charge of -1. And over here, this atom, 6 protons and 5 electrons, so it has an extra proton. This would be +1. And so we start looking at atoms to their overall charge, and we can start to describe materials as having charges as well. Just staying at the atomic level for a second, though, it's not enough to just be able to say, or it's not specific enough to just say -1 or +1. So we need to be able to have a specific value. And some very smart people figured out what those specific values are. So first, most importantly, the unit for electric charge is called the coulomb, after Charles Coulomb. And you can see he was a cool dude. He wears his hat backwards and has these cool sunglasses. He was pretty Charles Coulomb. And so 1 unit of charge is 1 coulomb. And that has a specific value. It's a number, 6.24 times 10 to the 18th. So this is a coulomb. We remember the mole, right? The mole is a number. It has a specific value. A coulomb is a number. It has a specific value. That number is 6.24 times 10 to the 18th. I would encourage you to write it in your notes, but it is also on your equation sheet. We know, so therefore, when we have extra electrons, we would say something has a charge of, say, -1 coulombs. Or if it's missing electrons, it would have a charge of +1 coulombs. And so that means we're also going to need to know charges of individual electrons. And so electrons are teeny tiny, so they're going to have a teeny tiny charge. A single electron, just one electron sitting here, has a charge of -1.6 times 10 to the -19th coulombs. Okay, so that's a teeny tiny charge because an electron is teeny tiny. 10 to the -19th. It turns out that if I have 6.24 times 10 to the 18th electrons, then I would have a total of 1 coulomb of charge. So it takes 6.24 times 10 to the 18th, or a coulomb of electrons, to give me a -1 coulomb charge. If obviously electrons and protons are equal in number, then there is no charge. And so if an electron has this negative charge, a proton has to have the opposite charge, but just positive. So a proton must have a charge of positive 1.6 times 10 to the -19th coulombs. And so therefore it would take me 6.24 times 10 to the 18th protons to have a charge of +1 coulomb. And then neutrons have no charge, so they would have a charge of 0 coulombs. Again, these are values I would encourage you to put in your notes, but they will also be given you on your equation sheet. So what does that matter? Well, so now we can start looking at the total charge of an object, because very rarely are we looking at a single atom. We're looking at a whole object, a metal plate, something along those lines, which is made up of many, many, many atoms that can give up many, many, or accept many, many electrons. And so we need some way to calculate the total charge of an object. And the total charge, or Q, is determined by taking the number of excess electrons or protons and then timesing it by the charge of a single electron or proton. And so the total charge of an object is just how many electrons it's missing or has gained times the charge of a single one. And so we can do some examples here. A sweater has an excess of 4.67 times 10 to the 10th electrons. What is the charge of the sweater? Well, the total charge is going to be equal to the number of excess electrons. So in this case, 4.67 times 10 to the 10th times the charge of a single electron, which is negative 1.6 times 10 to the negative 19th coulombs. And so if we put that in our calculator, I would encourage you to do that. We get negative, negative 7.47 times 10 to the negative ninth coulombs. So still not even a full coulomb of charge. We could do this another way. A balloon has lost. Okay, so it's important to think about this. A balloon has lost. So here's my balloon. It's got electrons and protons filling it, and so we steal some of these electrons from it. So if we're taking electrons from it, overall we're going to be end up with more positive than negative charges. So we would say that this, if it loses 3.5 times 10 to the 8th electrons, then that's how many more protons it's going to have without an electron. So now we would do this. The total charge of my balloon is, it has 3.5 times 10 to the 8th extra protons times the charge of a single proton, 1.6 times 10 to the negative 19th coulombs. And so the total charge of this sweater is going to be, I end up with 5.6 times 10 to the negative 11th coulombs. Okay, that is a small number. Maybe just to give you some idea, when we go back here and we talked about this, a coulomb of charge is actually rather a lot. We'll talk about amperage and electricity coming up, but a coulomb of charge is actually a lot. And so it would be enough to hurt you. And so while this is still negative 11th, 5.6 times 10 to the negative 11th coulombs, this would result in an object, a balloon, that has some electrical charge to it that would be detectable. Okay, so what does this mean in terms of charging objects? So one way to charge an object is to, well, I guess we should say an object is charged, as we just saw, when it has missing or extra electrons. And so one way to get electrons to transfer from one object to another is to actually rub them together. And so maybe in middle school or even elementary school, your teacher did a thing where you like take a plastic rod and you rub it with fur, and then they become electrically charged, and that's called charging by friction. So physical contact allows electrons to move from one object to another, and that results in two charged objects. I think this is something that we're familiar with when you like rub your foot on the carpet, right? And so here's John Travoltage here. And so when you rub your foot on your carpet, that rubbing together is causing electrons from the carpet to accumulate in you, which ultimately gives you an electric charge. An important thing to know is that charges are conserved, right? Electrons can't be created or destroyed. They're simply moving between objects. And so the electrons from the carpet are now in John Travoltage here, but they are still there. We haven't destroyed or created any electrons in this process. Why does this happen? Well, the charged atoms or molecules interact in predictable ways. Again, something that we're probably familiar with, like charges repel and opposite charges attract. So uh, if we go back to this picture, what you can see slowly over time is these electrons, right, negative charge, so electrons are moving away from each other. They're spreading themselves out. Well, why is that happening? That is because like charges repel. So if I take two negative charges and have them near each other, they're going to push away from each other. Same would be true of two positive charges, whereas if I have a positive and a negative charge, they would be attracted to each other. So this is an important rule to remember. Okay. So this can also happen in insulators as well, and that's called polarization. So let's go look at another example. Right, so I have a balloon. This is something we're all familiar with. If you have a balloon and a sweater, you'll notice that for every one of these protons or positive charges, I have a negative charge, right? That's true here. It's true in the balloon. And so I can do charging by contact. If I take this balloon and put it on the sweater and rub the two together, what am I doing? I'm actually stealing the electrons from the sweater and they're being transferred to the balloon. And so now what we have is the sweater is positively charged. We could calculate the value. And the balloon has a negative charge. So overall, because these are two oppositely charged objects, if I release it, it is attracted. Okay. To look back at our notes here, polarization is when objects that can't move are brought near each other. So for example, here. So now the charges, this balloon is rubber, so the charges don't move easily from it. And this wall is concrete, wood, whatever. The charges can't easily move from it. And so I want you to watch what happens to the atoms in this wall. Again, every electron and proton is paired. Now this is a very large, a strongly charged balloon. It has an overall negative charge. But since the charges can't move, when I bring this balloon near the wall, what happens to those other electrons? The electrons can't move. They can't be transferred back and forth because these are two insulators. And so the only, or what has to happen is the like charges will repel. The negative charges in the balloon are repelling, or repelling the charges in the wall. And so what ends up happening here when I hold it here is the wall in that area has a slightly positive charge because the electrons in there, which can move, are being driven further away because like charges repel. And so that is something that is going to be important moving forward as well. Right now, it's just important to see that those like charges are repelling. Okay. If we come back here, and so that is called polarization. And that's how things like a balloon sticks to a wall um, as a result of this, right? So now, if I bring it here, it's attracted to the sweater. Why does a balloon stick to the wall if the charges aren't moving? Well, this balloon is negatively charged. All those negative charges in the wall have moved away. And so since this balloon is negatively charged and this region of the wall is positively charged, slightly, they are attracted to each other. And so that's how balloon will stick to a wall. Or for example, bits of paper will stick to like a comb. Examples like that. Okay. Last thing we really want to talk about here is why does that happen? So a force we defined before, a force is just a push or a pull on an object that results when two objects are interacting. So why do positive charges move away from each other? Why do negative charges move away from each other? Why do like charges attract? Those are pushes and pulls, right? I mean, that's what's happening here. This, if I let this go, there is a force pulling these two objects together. Okay, and so, or there is a force holding these two objects together. But what's different is this. When we have always studied a force or looked at forces before, they've been a force where like I could push an object across a table. I have to put my hand on it and actually push it across the table. And yet, so there has to be a force here because these are pushes and pulls like we've seen, and yet they aren't touching. So that's what we want to look at in our next focus question is how can a force exist? Clearly it does. Pushes and pulls. These charges push and pull on each other and in turn whole objects without them actually touching. So that is what we're going to look at in focus question 2 is what causes electric force. So hopefully that helped. We ran through, this should cover all of the guiding questions for focus question 1. As always, if you want additional help or clarification on any of these, please review the text as well as other videos in the learning resources, and then feel free to ask any questions. Hope this helped.